Hello, my name is Eli Tannenbaum. I'm a senior at Pomona College, and I'm currently taking organic chemistry. And being a magician, I like to find ways to involve playing cards in just about everything I do. And organic chemistry is no exception to this rule. In fact, I've created an entire pack of cards that's full of different organic compounds, which you can see if you go through the pack here. And what I've realized is doing organic chemistry with playing cards is actually significantly easier than doing real organic chemistry in a lab. And it also, coincidentally, serves as a great study tool. So we're going to try to do some organic chemistry with this pack of cards. So you can take any two cards you want. For example, the top two cards in this case, a benzene and an acid chloride. And when we combine benzene and acid chloride, it's well known that Friedel-Crafts chemistry occurs. And playing cards are no exception to this. If we take the benzene playing card and the acid chloride playing card, give them a little shake, we can actually get some Friedel-Crafts chemistry to occur with our playing cards. You can see here we now have the products of that reaction. And of course, since we have 52 different organic molecules in this pack of cards, we can keep the chemistry going as long as we want. We can take this compound, for example, and if we combine it with our acylated benzene, we can actually reduce the carbonyl to an alkane, as we can see here. And of course, when we have an alkane, there's plenty of different possibilities of what we can do next. For example, we can take another card, for example, this acyl chloride over here, and since we already have an alkyl chain on our compound, we can kind of predict where this is going to go, that it's either going to go ortho or para. So let's see where it goes in this case. If we add the acyl chloride, give a little shake, we can actually get the acyl chloride to add para to the benzene ring. And once we have carbonyls, our possibilities are limitless. We can take the deck and search for our favorite reducing agent, sodium borohydride. And if we take sodium borohydride and we apply it to the carbonyl, we can get it to be reduced to, guess what? An alcohol. Ta-da! And of course, alcohols themselves are quite versatile, and we know how we can edit alcohols with PBr3. We can add PBr3 and get that alcohol to turn into a bromine. You can see here we now have a bromine. And bromines are great because they're great leaving groups. So we can take something that's a good nucleophile, like say NaCN. We can add it to our molecule that we have here. And if we do some addition or substitution in the center of the deck, give a little shake, give a toss, we can actually get our SN2 chemistry to occur. Because you can see we've now created a nitrile. And nitriles are simple enough to deal with. Our hands are slightly acidic because of the oils in them. So if I take my hand and rub it on this nitrile, we can actually turn the nitrile into a carboxylic acid. Now, you may be wondering, what is the purpose of this? Why have we chosen to do all this chemistry with our playing cards here? And the reason why we've chosen to do this is because the molecule that we made is actually not an ordinary molecule. It is actually, in fact, a molecule of ibuprofen, which we have here. We can see the playing card has now turned blank. We have now produced ibuprofen, which is good, because I haven't had my coffee yet this morning. And as a result of that, I kind of have a big headache that you can solve with a big pill of ibuprofen.